Right, hello again, and welcome to week 10 of the course. Well, here we have someone who's maybe going to help with the tech. I'm just going to pause the video. Okay, I return you from that sudden jump cut where we may actually have managed to fix the tech, which is going to be appropriate whether it works or not, because the lecture today is about things being broken, as luck would have it. So, as I said, this is week 10. In case I haven't recorded the numbers yet, I think it's 15 or maybe 16 people here. A slight improvement. And we're going to have more of you coming later in the week, because we're going to have to sort out something that I'll explain in the second half of this lecture that's going to require the people who are watching the video at home to actually turn up for a change. But we'll get to that next. So we're in kind of basically the last third of the course now, and there's a bit of a change of emphasis about to happen. But just as a bridge into that, I've got one little lecture for you about diagnostics. So, as you have probably discovered by this point... Oh yeah, screen's off. Okay, hold on. Good. Won't affect the recording, it'll just affect the people in the room. Fixed. So software is a complicated thing, as you're discovering. And you'll get it wrong. You'll make mistakes. Everybody does, even people who are really good, like me. The sad fact is no one really knows how to make software. That's my assessment of the situation, because it's a fairly new thing. You know, we've only been doing it at like a large scale since, you can maybe say, the 70s, and only from a really large scale in the modern sense during this century, when all the internet and stuff happened. And it's hard, and we haven't figured it out. There's this whole discipline of software engineering where we try to figure it out, but a lot of that stuff's really dodgy and doesn't work. But it's getting better. We're trying to find better ways to organise the creation of software, but it remains difficult. We're way behind the other engineering disciplines who can actually do stuff like, build bridges and skyscrapers actually stand up most of the time, whereas software has not really got that level of reliability or control yet. You could argue that software engineering maybe goes back 50 years. I think the term was actually coined in the very late 60s. But it's mostly like a 1970s idea that there would have to be such a thing as software engineering. We'd have to figure out how to make programs in some kind of reliable way. But it's still a mess. You look at any large software project, it will be over time and over budget, often by like factors of 3 is quite common. That's certainly true of games, and it's true of other stuff as well, just the way it is. And yes, not only are they slow and late and too expensive, they're also rubbish and full of bugs, and they don't do the things that people want them to do. Software is terrible. There will be bugs. So this is like the depressing fact of life as a programmer, that you spend a lot of your time fighting against problems and stuff just being broken in stupid and horrible ways. The only way I can try to put an optimistic spin on that is that, in a sense, this is inevitable, because if it wasn't broken, it'd be finished, right? The reason you're still working on it is because it's not done yet. If it's not done yet, that's because there's something wrong with it. Obviously, sometimes the something wrong is just incompleteness. You haven't done the stuff you need to do yet. But often the other barrier is the stuff that you think you've done isn't working the way it's supposed to, or the way the people who asked you to do it want it to work, because they miscommunicated their requirements or whatever it is. Or maybe you screwed up. That sometimes happens. So there you go. If software wasn't broken, it would be finished. So you're going to spend your professional lives dealing with stuff that is broken. Now, I don't want to. I'm not saying that to excuse a kind of sloppy mentality. And in the best case, the brokenness is simply that you haven't done things that you know you have to do. But bugs are also a big part of your life. And I won't say particularly difficult with games, but games have got their kind of domain-specific problems. So one of the things about a game is they're really very complex. You get very large numbers of objects, and they're dynamic. Things are happening all the time, lots of interactions. They're obviously they're real time as well. It's not like kind of business software where you type something in and you press enter and it goes to the database and it updates the stock inventory or something tedious like that, or it tells the people to send the package to the warehouse or something like that. Real time stuff has got like a lot of the stuff's happening. It's happening all the time, 60 times a second or more, times hundreds, thousands of objects. It's just a ton of stuff. and the objects are constantly moving about and mutating their state, and it's all complicated as hell. And systems like that are hard to debug. You think of a more conventional, like a business system where, you type something into a form and you press a button and something happens. It's sort of transactional, and you can kind of look at that and say, well, if you type this and then this has to happen, and you can see how it's boring, but you can see how you could get a handle on such things, and you just try it and does it work, and no, and you do it again until it does work. It seems tractable, but live complex simulations are kind of feel like a different beast to me. So one obvious thing is that kind of traditional debugging that you could do, like print statements, just logging stuff out while it runs, as you've maybe seen when you're doing your own little games. It's better than nothing, but the problem is if you've got a print statement in some like generic update loop, like say your bullet update routine because you're trying to figure something out, well, the problem is the bullet update routine runs 60 times a second, times as many bullets as you've got in your game, which might be hundreds. So you just get huge amounts of spam being printed out, and it doesn't really help you do anything. So you have to do horrible things like, make the print statement only print it for like particular instances. You have to add a whole bunch of if statements to try and stop your logging from overwhelming you. And it gets very annoying. The other thing that you sometimes do in general debugging is you use a debugger with breakpoints in it. Do you know about breakpoints? Yeah, so you just step through kind of thing. And that's okay for very small, controlled, localized pieces of code. But again, a piece of code that runs thousands of times a frame, and it's maybe 2 or 3 of those cases something is going wrong, but you don't know which ones exactly. It's like you can't spend all day single stepping through code that's running, thousands of times a second, or if you do, your progress will not be fast. So unfortunately, although you can kind of single step your way through a transactional thing, it's not really easy to single step your way through a piece of like random game logic. So the problem is that the old style diagnostic tools that work okay for some things tend to not work so well once you scale up to the environment of a game. So I think the key thing to realise is that simulations and games have got this problem where there's lots of dynamic state and lots of stuff changing over time, and I think you need to have diagnostic support that fits that domain. So that means you want to have your diagnostics be visual and interactive and dynamic in the same way that the underlying system is. So you have to basically write a whole bunch of stuff to help you debug the system that'll actually let you get your work done. So the kind of thing I often add in a game is I'll have something when you're playing the game in developer mode. There'll be a thing where you can click on any object and it will send like a ray from the camera out into space to find that object. And then once you've picked that object, it's got a method on it, to print its debug state, and you just have that get written out into like a little overlay window or something. So it means you can click on things in the game to see what they're up to. So you can click on an AI guy, and he'll basically dump out, what he's thinking. Like it'll tell you, well, I'm route finding, and here's the place I'm trying to get to, and here's why I can't get there, or something like that. Or I'm targeting this guy, or I'm on stage 3 of the mission, or whatever it is that they're doing. And similar things with like collision systems, you could tell things to show you what their actual collision volume is to make sure that it's doing the right thing and they're positioned in the right place. So stuff like that you do quite often. Another thing that you see a lot, this was kind of started by things like Doom and Quake, where if you press escape it brings up a little text console where you can type in commands, and it turns out that was originally a developer aid. And when you're running it in developer mode, you can type stuff in there like, draw wireframe mode or, spawn new objects or this kind of thing. So the various things you might want to do during development and testing that require kind of special privileges. And you just write a little command line as part of your game that lets you make those things on the fly so that you can test them without having to, rely on them just happening kind of naturally. Like, you might want to check out how a particular entity behaves in a certain environment. Instead of having to wait until it naturally occurs, you can just spawn the object or spawn many of them and contrive scenarios that you care about. And then if you want to see what's going on, you can do stuff like, switch on and off different rendering modes or switch on and off lights dynamically or something if you want to see what's going on. So you do that kind of thing quite a lot. So here's just a simple example from Eve, where we've switched on the collision volumes that this ship has got, so you can see the underlying crude spherical entities this is maybe not just the collision volume. I think some of this are the orientation points, which is slightly different. But you can see just these kind of ghosty, transparent things here are just being drawn to show position and orientation information on various maybe special attachments that are on the ship. And that, I think this one here, the kind of wireframey one, is indeed an outer collision volume, a sphere that just about fits the spaceship. Not quite, never mind. Somebody will fix it one day, maybe. So this is the kind of thing you do a lot during development. The interesting thing is that this isn't kind of obvious to everyone, especially if you're just kind of self-taught and you try to like reverse engineer how a game works, because often this kind of stuff is taken out of the game at the end, or it's hidden away either so that you can't access it, or we actually compile it out at the end to save space and stuff. So all these kind of diagnostic features, they're an important part of building the thing, but we take them away at the end. So you might not realise they're important. And if you were like building up a task list, working out, what are all the things we want to do in the game, you might be inclined to focus on obvious user visible features, but forget about things like diagnostics. But they're actually really important because they save you time. You know, you have to put time into making them, but the idea is that they pay off because they help you debug the inevitable problems. So it's kind of like scaffolding. You know, that you put scaffolding up around a building to help you access it, to get in there and build it and modify it. But when it's all done, you take it away. That's kind of what diagnostics are often like. So here's another thing you can do in Eve. It turns out the objects in Eve have got like a huge bunch of like special magic parameters and everything. It's not like an ordinary object in a kind of like a class-based language. You have a class and it's just got a bunch of data members and you can kind of know what they are. Eve's actually is super dynamic. Each object in Eve has got its own set of attributes that kind of depend on its own unique qualities. So it's very much like a JavaScript object in that it's like a dictionary system. Right? They've just got like a whole bag of properties, some of which are conferred on them by other bonuses, some of which are intrinsic. So what you often do when we're trying to debug the game is you select an object and then you go to this inspector thing and it tells you what the various attributes this thing has. They've all got numerical IDs for looking them up in arrays and stuff like that. And they've got values, and there's the client-side value and the base value that's maybe been modified and all this kind of stuff. And you have to go through and like make sense of all this while you're developing it. So that's some of the stuff that you do. So I mentioned right at the start that obviously the very baseline diagnostic facility is just like a print statement or a logging statement, and we use that too. But the problem with games is that often the log code is going to get executed very frequently, so it generates too much information. But you can either do things to make it like only emit the log on particular entity IDs that you maybe care about, or do some stuff to make it only emit the message once, or you just write it all out to a big giant log file and you have a log viewing program that lets you scroll through the log so that the fact that it's creating hundreds of lines a second doesn't matter and you can just focus on the bit you care about. So this is an example of some real debugging I had to do some time ago. Most of my additions have got the pat prefix, which I put on it, so it's easy for me to grep to find the lines that I've added as opposed to other people's nonsense. And you can see this kind of stuff that's going on. We're creating objects, and I had to add a bunch of like wrappers to let me see that various special things were happening, and the number of asterisks here reflects the depth of nesting, because this is like some horrible recursive monstrous thing that's going on. So this is me tracking the start and ends of various actions in the system to make sure that all these modifier numbers get calculated at the right time and they go to the right place. And it's all fucking atrocious, but that's life. So the other thing you can do, I'm quite keen on, is a thing called debug pages. The idea here is if you've got like an important manager object, like an entity manager, again, you often want to know its state when you're playing the game to figure out what's actually happening. But you don't want to just, as I say, you don't want to just have to like break into it in single step and inspect data structures. So what you do is you have these managers are able to, again, write relevant information about themselves to like a special window I call a debug page, just a simple overlay on the game. So what you can do is you can pick any of the managers that you care about, and they just write their information to the screen, telling you like how many entities are there and what type are they and what order are they in and this kind of thing. Stuff that you'd want to maybe know when you're analysing the system. Eve itself has got some other variants of this, like because Eve obviously is like a client-server game, so a lot of Eve runs on servers that don't have displays. You know, they're just big box computers in a data center somewhere. So what they do is that they write their information out. Actually, the HTML files, they've all got a little web server running inside them. So instead of printing stuff to the screen, they write it out as HTML, and then we remotely connect to those machines and browse them as if they were a website. And you go to that page and it lists all the internal details of what's going on the server. So that's one of the things that Eve does to expose its state to the developers, so we can figure out what's happening to the servers when shit's going wrong. So with the debug page thing, this allows you to look through your manager objects and see what they're doing and look at their internal data structure. So that's why I made you do the thing where you draw the little red circles on the spatial manager. That's like a super simple version of this. Like a real spatial manager would be like an octree maybe, and it would have quite a lot of complex internal structure and a bunch of objects in it and different sizes of cells and stuff. And you would definitely have a mode on your octree where you'd like press a key or type something in, and it would actually draw those structures onto the screen, so you can see, this part of the octree is being very heavily decomposed, and this part isn't, and this part's, and see where the objects are registered. So by drawing those little red circles, that's you doing like the simplest version of visualizing that structure, so that you could see whether it's right or not. Because the idea is, if it's right, the red circles and the actual objects will be on top of each other. But if you do things like, forgetting to unregister, or you register at the wrong coordinates, you'll see things like the circles and the objects won't match because they're not in sync with each other. And this is how you see that you've made a mistake. Yes. So when you've got these kind of visualization tools, it makes it a bit easier to see what's going on in a system that's otherwise like super complex and full of lots of dynamic nonsense. And this lets you kind of probe into the system while it's running, so you can do things like selecting particular manager, or go to the entity manager and cycle through a particular object, and you say I want to pick that object, and then it'll dump out its information about its position and its internal state, and that'll give you some idea as to what the game is doing. So this ideally is going to help you localize the cause of a problem. If something's misfiring, like an enemy's not attacking properly, you go and select them, and you get them to dump out their info, and you see, he's not attacking because he's in fear mode. He got stuck in frightened mode, and he's trying to route find back to his home base or something, and he's never entering attack mode, and you try and figure out why did that happen, that kind of thing. The other thing that's less depressing than some of these other facts is that when it comes down to it, a lot of bugs turn out to be quite simple. They're fairly obvious once you've seen them. The problem is seeing them. So the difficulty can often be localizing the problem, so you can zoom in on it. But once you've done that, it often becomes fairly apparent that it was just some silly mix-up. An X and a Y got swapped, or you set something when you should have incremented it, or you negated something that you shouldn't have negated. Things like that. So if you have good diagnostics, it makes it kind of easier to find these things. But not always. Some things are actually hard. You will occasionally encounter that. One of the particular problems is that in real game development, you sometimes get bugs that happen, from time to time, but nobody knows how to reproduce them totally reliably. It's a bit like it breaks sometimes based on some condition that hasn't been properly recognised yet. And that's really horrible, because when you get told a bug like that, if you can't reproduce it, it's very hard to see what's going on. And even if you do occasionally reproduce it and think you've fixed it, when you retry it to see if you've fixed it, you don't know if you have fixed it, because it only happens some of the time anyway, right? So it's actually one of the key things is if you've got a bug that's not very reproducible, you want to make it reproducible, first of all, so that you can actually see it in order to think about it and work on it, and also to verify that when you think you've fixed it, that it actually works. One particularly vexing problem that comes from unrepeatable bugs is something that we, in the trade, call a Heisenbug. Do any of you heard of a Heisenbug? You know what that is? Nobody? Okay. But you know who Heisenberg was? Not the guy in Breaking Bad, the physicist who he's named after. So a Heisenbug is named after Heisenberg, and it's a kind of a bit of a joke at the idea of the Heisenberg uncertainty principle, all this stuff about measuring position and momentum at the same time. They're actually like formal and informal versions of the Heisenberg principle, but this is an allusion to the informal idea that the fact that measuring things changes them, which is one of the Heisenberg things. So a Heisenbug is a bug that appears to disappear or alter its behavior when you attempt to study it. So the classic thing is here, you've got some bug going on in your system, and you think, oh, it must be in this function somewhere. So you go in and you write some diagnostic statements, you print some stuff out or something, and then it goes away. It's because you've looked at it. And then you take the print statements back out and it comes back. What could possibly cause a thing like that? How the hell can that happen? Or you have a bug where it's like, you try and, if you try and do any diagnostics on it, it actually stops happening. Do you have any ideas to how that could ever be, other than the universe is out to get you? No? Well, there are various ways it can happen. One is if you're doing stuff in languages like C and C++, where memory allocation is a very important thing. One of the things you can find is that when you investigate a bug and you add diagnostic code around it, even if it's just print statements that shouldn't really do anything, the problem is they change the location of things in memory, right? They shuffle the code about. You used to have a piece of code, now you get a piece of code that's got some calls to a print function in it, so that function is slightly longer than it used to be, and it's going to be in a slightly different position in memory. Well, it turns out a lot of bugs in C programs are about invalid memory accesses, people referring to pointers to dead objects, or accidentally running off the end of arrays and stuff like that. And all of that stuff depends on the very particular layout of things in memory. So often when you start adding diagnostics, because you're moving the code around, and maybe even the data structures move a little bit, just because they end up having to be allocated differently, things that end up in different places. So that thing that used to be, scribbling over some random address in memory over here, is either scribbling over a different random address in memory, or the one that it was scribbling in doesn't contain the important thing anymore because it moved. So it's often things moving around in memory can make the bug appear to shift while you're analysing it, which is incredibly annoying to deal with. That's, as I say, you tend to get this more in the kind of compiled static languages like C and C++, less so in dynamic ones where that kind of memory fragility is not so common. But you could probably get it in any language under some circumstances. So one of the big things that you want to have as a developer is to be able to reproduce stuff so you can deal with these weird problems. So the classic problem is if you have a bug that is, it's rare-ish, but not so rare that it can be ignored. It's just rare enough that it doesn't happen all the time, which makes it very painful for you to debug it. They're a real killer of a thing, and I've definitely found those to be a problem on real games, trying to ship real stuff in the world, where you have this annoying bug, and it's too frequent for us to be able to just hand wave it away, but it's also rare enough that you could spend a day debugging and not actually make it happen. Very annoying. One of the things that's actually done for this, because the classic claim is that the tester will say, oh, there's this bug that happens from time to time, and the developer will say, works on my machine. And there's this kind of problem. It's like, it is your responsibility to investigate and fix these things, but at the same time, if you can't make it happen, it's like you can't see what it is. How are you going to do anything? So one thing that QA departments used to do, in fact, back in the ancient days in the 90s, what they would do is the QA people would have a VHS machine, a video recorder, connected up to the system, and they'd actually be permanently recording what they did on videotape, so that if they got a bug, they could at least send you a video cassette and say it happens at 2 hours and 18 minutes into today's videotape, and you could at least see, oh, it really did happen, and then you have to figure out how the hell to duplicate it. And of course, nowadays they can often do that by just having video capture built into the test machine, so they're constantly running any kind of video capture program, so that if a very fairly obscure bug occurs, they can at least confirm, look, it still happens. It hasn't just gone away by magic. So that's one thing that's done. But the thing that I prefer to do that's a bit better than relying on just having video recordings is diagnostic replay systems. So this is kind of like the holy grail of debugging. Imagine if any time a tester had a problem, no matter how obscure it was, they could basically give you a file that would make that happen again on your development machine, so that you could catch the repro. Can you actually do this? Sometimes you can. I have sometimes been able to make this work. So a lot of the games I've worked on, there's been a thing where when, you know how I talked about the gather input stage, which we actually don't do very much with in this course because our inputs come from the event system usually, but if you record those events somewhere, you can basically take any of the inputs that the user is providing and remember them and ultimately write them out to a file. So if you do that and you have a game loop that's kind of well designed so that all the user inputs get kind of recorded somewhere, the theory is that you could then run the game in a mode where instead of like listening to the real inputs from the real keyboard, it would load them back from file, and on every frame it knows what keys got pressed and it just injects those back into the system. And if you write the code well enough, that will actually reproduce exactly what happened when the person was playing the game. So for the cost of a fairly modest file that just records, on each frame what input was actuated, then you can potentially replay the whole logic in a way that you can not only see the bug, but you can then actually start doing things like single stepping through it, which is really cool. So that's kind of one of the reasons I say that gather inputs is a separate step, that you do all your input gathering at the top of the frame. Part of the reason for that is it's just good practice generally, but it also gives you a place where, having done that, that's where you would save the inputs. You would write them out to the replay buffer or the replay file, and that's also where, when you're in replay mode, you would read back in from that file and suck the inputs back out in order to get your playback system to work. So if you want to do this, you want to be robust, you have to be very precise. So you have to make sure that all the inputs that come into the system get recorded. If you forget one, then it's just not going to work. Even a fairly small error will invalidate the replay and you won't get the right behavior. It's easy to forget things like time. Like, imagine if you get a piece of your code that interrogates the system clock or something like that. Well, when that runs live, if you look at the system clock to measure something, maybe you've got some game logic thing that depends on it, that will be based on the actual time, like right now. In a replay system, you actually need you need to reproduce the old value of the time, don't you? Because it might make a difference. Imagine if for some reason your game had some logic that only does certain things on a Wednesday. That would be quite strange, but a computer program can do that kind of shit if it wants to. So you have to kind of make sure that during playback mode, it's always Wednesday, right? So you end up having to wrap up a lot of operating system calls in these wrappers that make sure that they produce repeatable results, even for things that you might not expect. The other classic one that happens more commonly is random numbers. So as you hopefully know, random numbers most of the time aren't really random. They're just arithmetic sequences, depending on an initial value and some stuff. But you need to make sure that initial value is the same for every run of your game. Otherwise, your randomness will be different, and then, of course, all the behavior will end up being slightly different. So when you're doing this kind of system, you need to make sure that at the start, you actually know what seed your random number generator is using, which it might not be up to you. It might be what one system provides. But you have to kind of get hold of that and write that out to your replay file so that when you play the game again, all the randomness happens. All the randomness happens in the same way. And there are other problems like asynchronous loading, where you say load this file and it goes off to a disk that takes an uncertain amount of time and it comes in, some number of frames later, you don't know how many. You need that to reproduce as well. So it means that your asynchronous loads, you have to, when you're doing it first time through, you have to say, okay, I asked for this on frame 5 and it arrived on frame 39, and you have to remember that. And on playback, you have to kind of get to frame 39 and then wait until that resource is actually loaded back in so that it behaves just the same way as it did. This is when it starts to get difficult, unfortunately. But it's what you have to do if you're going to do it. The other big problem here is threading, which is a big thing now in modern games where you have to be very parallel and have lots of threads going on. That's really hard to be able to reproduce it because, as you know, the operating system switches threads whenever it feels like it based on stuff that you don't know about and you can't really control. So if you have a piece of logic that depends on whether thread A or thread B finishes first, that won't reproduce automatically. So you have to do things like, you have to have some kind of synchronization points if you've got a multi-threaded game where you say, well, this thread does all this stuff and you do all your stuff, and then at some point we agree in what order we're going to look at the results. And again, you have to remember that in your replay system, otherwise it won't actually work. So the sad fact is, replay systems used to be a great idea, and I was very fond of them, but as time goes on, it's getting harder to make them work. It's hard to make games be deterministic in that sense. But if you can do it, it has advantages, because it does mean that you have this great gift that whenever you get a really obscure bug, you can just tell the tester, send me the replay file, and then you can play it through and you can see what happened. There's some other things you have to do if you want replay systems to work. Not only do you have to capture all the inputs and all the relevant external state, like the random numbers, the async loads, the arrival of network packets, all that has to be recorded as well. You also need the game logic itself to be deterministic. It has to be something that, if you put the same inputs in, it will always produce the same outputs. You'd think code would be like that normally, but it's not always, because of like weird, silly things that people do. So if you have a replay system, you have to make a kind of you have to make a commitment to making your game logic repeatable. And the way you want to think about that is your game becomes like a state machine, where it's like whatever is going on in the world, that's your state, and new inputs come in, whatever they might be, and then they cause you to evolve to a new state. And you need to think of, like, that's exactly how it must work. It's not allowed to do any other crazy shit, like, going and secretly, talking to other computers over the network and not recording that data, because if you don't record the data, it won't reproduce. Also, if you have bugs in the program, if you have things like in C, if you've got like array overwrites and stuff like that, they don't necessarily reproduce either, because memory layout isn't something that you can guarantee will be reproduced. So occasionally there are certain types of bug that produce non-reproducible behavior because of the kind of turbulent nature of memory allocators and things. So you have to watch out for stuff. But if you do that, which you can do, and I've done it on real things, you can create a system that is sufficiently deterministic that you can just say, I want you to go into replay mode now, where you suck all your inputs out of a file, and it just does all the things that it would have done originally, which is quite cute. The nice thing being that when you're doing the playback, unlike originally when the tester was doing it, because they maybe didn't know the bug was going to happen, and they're not on a, they don't have a debugger or anything like that. So they're playing through and they can make the thing happen, but they can't do anything about it. But when you're doing the replay, you know what's going to happen. So you can do things like you can breakpoint it a couple of frames before the bad thing happens, and you can go in and you can look at the data structures and you can kind of see maybe, oh, look, there's a division by 0 here. That's why it's about to blow up in a couple of frames. So it's a really useful technique sometimes. Yes, so one key aspect of making a replay work, you basically need to make sure that the update and the render are very separated. That you don't do things like, and occasionally some games do this, unfortunately, they do things where, like, in the course of rendering something, they actually like change game state. So maybe they use the rendering routine to work out visibility checks or something like that, and then the visibility checks affect the gameplay. You don't really want to do that. Ideally, you want rendering to be a purely cosmetic activity that doesn't change the state. You just want it to be, it just draws pictures and doesn't do anything else. That way, when you're doing the playback, you can have the playback be rendered from like different points of view. If you're trying to see what's going on, you can move the camera around on the playback and it won't affect things. But that'll only be true if the rendering doesn't affect the logic. And you kind of want that to be the case, because during the playback, when you're investigating a problem, stuff like moving the camera around is exactly what you want to do. Or you might be in a debug mode where, when you're playing it back, you tell it to like render the stuff in wireframe, or to like use different shaders or something, because that's what you want to look at. So you need to be sure that that kind of stuff won't break the actual game logic. So separating the update from the renders is a very good policy. So if you do that kind of thing, and if you have like your debug pages and stuff like that, you need to make sure your debug pages are just writing stuff out and they don't modify things, at least not in ways that you don't know about. That way you can run the diagnostics during the playback and it won't actually change things. It won't cause Heisenbugs, right? The problem is if you don't do it right, your debug pages, if the course of in the course of writing this thing out, if you reset some flags or something like that, the problem is it'll now change the behavior, and you're back in the land of confusion. Yeah, so these are the kind of things that you might want to be able to do during playback to help you investigate it, and you want to make sure that those things don't screw up the game. One of the key ones, by the way, which I maybe forgot to mention earlier, is the delta time values. Right? When you're playing something back, if you just looked at the real system clock to look at the time deltas, they would be variable and it would depend what you're doing, and especially if you're pausing and single stepping during playback, it's going to be very different. So one of the first things you have to remember in your replay thing is you have to actually write out what the delta t value was for every frame, because you have to use exactly the same delta t's, otherwise you won't get the same result. Yeah. So it turns out it's actually quite tricky to do all this. With some reluctance, I would say on a very modern game, maybe it's not going to be worth it. It's something that I generally did this throughout my career, but I haven't been able to do it at CCP. Eve operates in ways that would not make this viable. And even the game I did before that in Scotland, it was an MMO game, and it just got a bit too complicated, too multi-threaded, too much network stuff, that it wasn't really possible to do it. But on many of the other games that I've worked on, I did in fact write a replay system, and we used that to debug stuff. There was another game called Crackdown. I don't know if you remember that one, but it had a replay system built into it that I actually used to fix some really gnarly bugs towards the end, very hard to reproduce things. And in fact, the replay system helped us to knock those on the head and get the thing into an almost releasable state. So yeah, it requires a bit of discipline. Some of that discipline is good for you, like separating logic from rendering, being very aware of where your randomness is coming from, is actually quite good practice to just make sure that you understand what your code's really doing. The other cool thing about replays, you can potentially make them self-checking. So if in addition to recording all of the input state, if you say like maybe every 30 seconds you write out the positions of your objects or something as well, then the point is during playback, it should be able to check that the position it arrived at is the same as the one that you snapshotted during your recording. You know what I mean? Yeah, you just like every so often you would dump out the XYZ coordinates of your entities, and then during playback you make sure that that's the same, because if it's not, it means that something diverged in the system. And you can do that too, and that makes the replays kind of self-checking, so they can identify if someone has indeed done something like an unhygienic random number that would actually screw stuff up. So that's a thing you can do. You can actually dump out state snapshots during the game. The other good thing about a self-checking system like this is it will catch things like problems with uninitialized data in C, where you can allocate variables in C and not initialize them, so their value will just be whatever that memory location happened to hold, which is essentially random, sort of. And that happens quite a lot. So a lot of bugs are sometimes just uninitialized memory. If you do that in a replay system, and you make it self-checking, the replay system will just tell you that the state diverged. And one of the things that might be implied if there's a divergence is that you've got some uninitialized memory or something. Another cool thing you can do with replay systems, if you've done it right, if you've made sure that the rendering doesn't affect the logic, is you can play them in fast forward, which is good, because maybe you've got a bug and it took like 45 minutes of playtesting to find it. You don't want to have to spend 45 minutes playing through it to get there. So what you can do is you can just tell it when it's doing the playback to not render for the first 44 minutes, and it'll just skip over the rendering logic. So it just runs the game update. And usually the rendering is the slow thing in a modern system. Most of the time spent on the rendering, not so much on the game logic. So if you do that, you can kind of fast forward through your 40 odd minutes of playtime in a minute or something like that, which is much more practical. And you can either you can tell it to just render like once a second or something, so you can see roughly what's going on, or you can tell it to not render at all until it reaches a certain timestamp and then start doing the renders. But that only works if the renders don't affect the game logic, which is another good reason for making it be that way. That's what I just said. Yep, and I did actually use this. On Crackdown, we had a very nasty audio bug that was in fact caused by a mixture of uninitialized memory and an array overwrite inside the audio driver, which was also slightly dependent on thread timing. So it's like all the evil stuff happened all at once, and that made the bug quite hard to reproduce. It only happened under very, particular set of circumstances, but often enough that it was, unacceptably frequent because it was a crash bug. And luckily, I managed to get the replay system to catch it a couple of times, and we did this thing where we could fast forward through the replay system up to, like a couple of seconds before we knew the crash was going to happen, and then we could get in and look at the code very carefully, and we started to realise that, we're overwriting a buffer here, and it only happens sometimes because it depends on this thread finishing before this thread. We managed to figure it all out and undo the damage and repair the whole thing and make it work so that we could ship the game. So fast forward is one thing. Maybe rewind would be cool as well. You'd like to play a replay, and if you kind of go past the point where the bad thing happened, can you go back to like try again without having to do it again? As is usually the case with rewinds, no, not really. It doesn't work by magic because that's how time works. But if you really wanted to, you could almost make it work. The problem is that game logic is not reversible. That's why you couldn't just change your delta t's to be negative to make all the action go backwards. Back to the Dead Island video. But in theory, if you also dumped out the full state of the game, let's say every 30 seconds or something, then you could potentially have a system where you could say, okay, I want to go back to 30 seconds ago, and you would just tell it to go back to the state snapshot that it took 30 seconds ago, and you could play forward again from then. So you could have a limited type of replay if you wanted to try some particular thing over and over again while you were debugging it. But that's not really done in practice. It could be done in theory, but I don't think it would really be worth it usually. Yeah, so this is sort of the idea, but in theory you could do it. If your game was simple enough, you could maybe dump out copies of the state every so often as a snapshot thing. But if your game was that simple, you probably wouldn't really need a fancy debug system, so it's a little bit of a borderline case. Yeah. The thing that's more likely to happen in practice is rather than using perfect state dumps, you just use approximate ones where you just dump out positions and stuff. And that allows you to just do the basic sanity checking, but it's not enough to let you reproduce things because there's more to an object state than its position. So it's not enough to just record the position. You need to have the velocity and the internal state of the AI or anything else that's going on. It just gets too hard. Yes, so much as I quite like replay systems as an idea, they've become less practical in recent years. In part, things like big MMO games where there's you're having to coordinate. You get servers and clients, and you need to kind of make everything work, and you get huge amounts of network traffic. And a replay system would have to record all the network traffic that comes in. That's what Eve would have to do, and it's just too much. It wouldn't be practical, so you can't really do that. And the other thing that makes it hard, even on kind of single-player games, is that increasingly there's so much multi-threading going on that games aren't very deterministic anymore. That technically, their behaviour ends up depending on thread synchronization events that are kind of in the lap of the gods. So that's unfortunate. Having said that, I think depending on unpredictable thread scheduling is a terrible idea. We shouldn't do it. But obviously you do have to exploit parallelism for performance reasons, but what you want to try and do is have a system that's a bit more like doing kind of independent jobs where you can reconcile the results in some defined order rather than having a bunch of threads that are all manipulating shared memory and you're having to make sure that you hold locks at the right time and all this kind of stuff, which is very error prone, very easy to go horribly wrong. I think at some point we're going to have to find smarter ways of doing parallelism than we currently have. Okay, so that's nearly that. The general point here is that diagnostics are important and that they will be a big part of your life because it's always broken. If it's always broken, it's worth spending some time building the scaffolding that will help you inspect it when it's broken. And it's one of these things that it might seem like, why am I going to spend a couple of days writing this, debug infrastructure? In my experience, it's always been worth it. It's saved you the time that it took to make the thing. And if you've been at all sensible at what you do, and if you have a little bit of experience, you kind of know the sort of diagnostics that are going to help, and you realise that it's worth putting these debug pages and console commands and stuff in just to help you in the course of development. Yep. And the kind of fancier part is that in theory replay systems are like a magical way of helping you do good reproducible behaviour in a system. And it's a nice idea to think about them and to know in theory how you could maybe do them, although whether you'd actually do them in practice, I got to admit, is less certain these days. It's maybe getting to the point where they're a theoretically interesting idea, but they're maybe not practically as useful as they once were. However, one thing I'll say is that my personal experience has been I'm often quite good at doing diagnostic stuff, and it allows you to solve like really hard problems, like super obscure bugs that people can't figure out, that are like really complicated and hard to get a grip on. Diagnostics are a great way of getting you into the innards of a thing and letting you figure out what's going on so you can fix it. Replay systems, when they work, give you kind of miracle powers to solve bugs that were otherwise just almost not going to be possible to figure out. So, if you're careful with these things, it can make you be very effective. All right. And if all else fails, if all these clever techniques of trying to investigate problems don't work, there is a secret technique used by certain highly functioning experts that I'm going to tell you about. It doesn't always work, though. It only works if you're good. But there are some people who can apparently fix things using a technique called percussive maintenance, which I'm about to explain to you now.
What's wrong with that thing, Jones? It's not working. Engine work starts up. Some trouble. Now I'm going to have to take it all apart and examine the voice circuits. The disc is in there.
My old grandma used to say, anything mechanical, give it a look back. Right now.
Try it out.
And that's the end of that.